Acoustic measurements with sine sweep method. In case you want to measure the acoustics in a room, this could be a classroom, factory hall, or an auditorium, you need a sound source, a recording of that source in the room in question, and some calculations to be made based on the recording. The same goes for measurements of acoustics between rooms, through walls or windows. In modern acoustic measurements, you can use the sine sweep method. The sine sweep method makes the speaker have a high sound level per frequency band, giving a good signal-to-noise ratio, and it is generally superior at suppressing background noise and distortion. To calculate most acoustic parameters, you need what is called an impulse response to be measured, here meaning a recording in a room where an impulse is created. The impulse, also called Dirac signal, is a sound signal that, in theory, is infinitely short and infinitely loud. In practice, a Dirac signal would be similar to a clap or bang. In some practices, especially earlier, this signal was made with a hand clap, popping of a balloon, or by firing a starter gun. This generates a noise that is then reflected by walls and influenced in other ways in the room, before it reaches the receiver position, the microphone. The recorded sound is called the impulse response, the response the room gives on an impulse. This is then transferred to a software and a computer for calculations. When you record this impulse response, the first thing that reaches the microphone will be the direct sound, if there is a line of sight. This will, in most cases, give the loudest sound level and generate a large starting peak in the recording, the direct clap or bang. After that, you would have the reflection of the bang from the walls, ceiling, floor, and objects in the room, giving smaller following peaks. There will be many peaks, positive and negative, because it's sound pressure. Here you see how an impulse response is visualized. So the response the room have to an impulse, a clap, pop, or bang. From the impulse response, a curve can be calculated of the sound level in the room over time after the impulse, and often this is done for each octave band individually. And from these curves, the acoustic parameters can be derived. This could be the reverberation time, but there are many other acoustic parameters as well that can be calculated from the impulse response. The reason why the peaks will be lower and lower is because the surfaces in the room will absorb some of the sound, and each reflection will be lower and lower, the more times they are reflected and the longer the distance they have traveled. However, using balloons, clapping, or firing a starter gun contains a number of problems that have led to the development of the sine sweep method. An obvious problem is that claps can only measure room acoustics and not, for example, the combination of a PA system and room acoustics. This could be in a train station, music hall, or similar, where you want to measure the whole setup. Here you would need an electronic sound signal that you could send to the loudspeaker setup. A second problem is that it's impossible to reproduce both sound levels and directionality exactly the same for every measurement. Each balloon, blow, clap, etc. will have a slightly different directionality and sound level. This can possibly give inconsistent results. This could make one consider to play a direct bang or clap from an omnidirectional loudspeaker to measure room acoustics, or from the PA system if you are evaluating one such. An omnidirectional loudspeaker, or omnisource, is a loudspeaker that emits sound almost evenly in all directions. However, it will be difficult or impossible to play an impulse with high enough level to measure the room acoustics with decent results. And this leads us to the sine sweep method. So what is a sine sweep? A sine sweep is a signal you send to, most often, an omnidirectional speaker for room acoustic measurements. It can also be a PA system if you want to measure the impulse response of PA systems and room in combination. A direct signal, or impulse, contains theoretically all frequencies. In a sine sweep, you time stretch the impulse, dividing the frequencies over a short time interval like a few seconds. So it's a sinuous tone that starts at one frequency and sweeps through all frequencies to an end frequency. You choose a frequency range that suits your purpose. Because it stretches in time, it can give a large output level per frequency from a speaker and lower the relative background noise level and improve the signal-to-noise ratio. For every doubling of sweep duration, the signal-to-noise ratio will be 3 dB more. When the sweep is emitted into the room by a speaker and recorded at the receiver position, the microphone, it is analyzed by a software. This process is really good at suppressing distortion products, whether that is due to distortion in the measurement chain or due to time variances in background noise. This could be turbulence in the room, people walking, or similar. To sum up, the background noise is suppressed by using a time stretch impulse because you get more acoustic power in the signal. Instead of one, you play thousands of samples. And the distortion is suppressed by the deconvolution method. Thereby, you have a really clean signal and accurate measurements. The outcome is an impulse response, and from here the acoustical parameters like T20, clarity, etc. can be derived. Thank you for seeing this video. You can see more at odeon.dk.